Hello. Today is the last lesson of this unit, which is quite exciting. It's quite a weird one, this one, and I've had a lot of people always say stuff like, "This is hard. It's quite hard to get your head around, and we'll see what we can do. Let's see how this goes." As always, we'll just do a quick starter. So remember, we did a bit of substitution. Have a go at this and see how it all goes. Okay, so quick reminder, when we talk about substituting, we're talking about how if x is 2, we're literally going to replace every x we see with 2. But it's not as simple as just putting it in there. It's one of those where you have to understand what was happening to x, what operations were happening, and then doing that when we substitute the new value in. So here, we can see that x is being subtracted by 3, so our answer is going to be 2, because x is 2, take away 3, right? So 2 take away 3, negative 1. Here, we've got 4x. Well, what does that mean? It means 4 times x, right? And our x is 2, so in our case, it's going to be 4 times 2, because when a number's next to a letter, it means times. Again, same idea here. A number's next to a letter, so we know it's times, and then we know it's going to be add. And again, BEDMAS exists, right? So you know division and multiplication happen before addition and subtraction, so that's why we do the 2 times, and then we add. So it's going to be 2 times 2, and then we're going to add 5. You know 2 times 2 is 4, plus 5 is 9. Be very careful here when it's 3x squared, because a lot of people think, oh, okay, it's being multiplied by 3 and then squared, but it's not. You have to do the exponent first, because BEDMAS, right, BE, exponent first, and then multiply it by 3. So this is actually going to be 3 times 2 squared. So do the 2 squared first, which is 4, then times by 3, which is 12. And then we talked about, okay, what if there's more than one letter? Or what if there's like a letter comes up twice? Well, it's the exact same idea, right? You've still got to just put 2 in as these values. So you're going to put 2 in here and make it get squared. And you're going to put 2 in here and get it to be times by 4. And then you're going to do it all together. Now, I tried doing this like by helping you, because we did 3x squared here and we did 4x here. But if you didn't notice that, it would just be 3 times 2 squared plus 4 times 2 minus 1. So 3 times 2 squared is 12. 4 times 2 is 8. Take away 1. And then just read left to right. 12 plus 8 take away 1 is 19. If you got all them right, you're the best in the world. If you didn't, don't worry. Hopefully I've explained it properly. Okay, so this, I promise, there's all a reason for my madness here. Let's just talk about this and see if we can get it done. So if we have a natural number below 10, and remember, if your natural numbers, it's over here, right? Any number that's higher than 1, so it goes 1, 2, 3, 4, 5, 6, or those are your natural numbers. So pick any natural number lower than 10. So let's pick, I don't know, 8. I'm going to call that A. And then we have an integer less than 0. So an integer again, integers down here, that can include any number that's like 0, 1, 2, or negative 1, negative 2, and etc. So I don't know, an integer less than 0, let's go negative 2, I guess. And let's call that B. Oh, what are we doing? Keep. Oh, why has it done that? No. I hate this thing. So recently, I think I said this before, it recently got an update where it thinks like by giving me the ability to rehearse, that's a good thing I want, but I don't, and I wish it could go away. Anyway, right. C, 2 numbers between 0 and A. So any 2 numbers between 0 and A. So I don't know, let's go 4, and we're 1, 2, 3. This is terrible. I should have done 5 or something, shouldn't I? Let's just call 3 and 5. Let's ignore the number line. And then 1 number between B and 0. So that was C and D. Between B and 0, let's do negative 1. And that's going to be E. And then the question is, could you give me 3 numbers between each letter? So that's quite easy here, isn't it? Except to be 6 and 7. Here it gets a bit confusing because it could be 4, but then you could pick like 3.5 and 4.5. And then you could do like negative 1.5, etc. And you can go do a bunch. The reason I said this is because we're looking for the idea that when we say numbers, a lot of people instantly assume you have to be like whole numbers, but that's not what we're talking about, right? We're talking about any number between these. And so when you start thinking about it, where is the most amount of numbers? Are the most amount of numbers to be between here, or is the most amount of numbers between here, or is it between here? And we're going to talk about that more in a second. So, just a bit of practice before we move on to this. Can you have a go at these questions here and these questions here? I'm going to go through this very quickly, but just have a go. It's me just practicing basically to see if you can do what I've just done here. So have a quick go. Okay, so state any 3 numbers between 0 and 1. That could be 0.1, 0.2, 0.3, or you could have been crazy and went 0.34521. Doesn't matter, right? State 4, rational numbers between 3 and 4. Just a quick reminder of rational numbers. It is numbers that can be written as fractions or of integers. You can just pick decimals for this. As long as it's a decimal that isn't a weird one, like pi or √2, it's going to be fine. So like 3.1, 3.2, 3.3, and again 3.45. And the reason these are all rational is because 3.1 is 31 over 10, right? 3.2 is 32 over 10, etc., etc. List all natural numbers from 1 to 5. All natural numbers, that's very easy, I think, because if you remember here, natural numbers, it goes 1, 2, 3, and then it goes up in ones. So is that easy from 1 to 5? I think it is. 1, 2, 3, 4, 5. And is this an easy task to complete? Yes. Why? Well, because I can do it. It's only 5 numbers, right? If I say try to list all the rational numbers from 1 to 5, though, is that possible? Well, no. Because, of course, I can have 1, 2, 3, 4, 5. But then I can also have 1.1, 1.2, 1.3. And you're like, well, also I could have 1.01, 1.02. And then I could have 1.001. And the idea is there's basically a ridiculous amount of numbers there, isn't it? And in fact, we say there's infinite numbers between there. And we're going to talk about that in a second. So is it possible? No. Why? Because there's infinite numbers. And it's supposed to say numbers. Imagine I could write. So it's not possible because it's infinite numbers. Can you list all real numbers from 1 to 5? Well, that's even worse, isn't it? Because real numbers include rational, but also irrational numbers. So that's going to be all the numbers we just talked about, 1.1, 1.01, but also all the weird numbers like pi, like √2, like √3, the numbers that go on forever and ever. So again, is that possible? No. Because there's infinite of them. And then we look at this. It says, how many natural numbers are there from 1 to 10? Well, natural numbers, that's fine. From 1 through 10, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 numbers there, right? Isn't it? From 1 to 10, yeah. And then how many whole numbers are there from 0 to 10? That's 11, because remember, whole numbers are basically natural numbers plus 0. How many rational numbers are there? Again, rational numbers are all the decimals that can be written as fractions, so that's infinite. How many irrational numbers? You can trust me, they're infinite. And how many real numbers are there from 1 to 10? Infinite. But what's interesting is we have this infinite, we have this infinite. Are they the same size? I don't know. And then this infinite. Is this the same size? Because technically this infinite, the real number, is this one plus this one, isn't it? It's the rational plus irrational. And if I'm adding 2 infinites, does that mean that this last infinite is the same size? I don't know. We're going to talk about it. Okay. So I've said the word infinite a bunch of times. It's about time we probably define it. So here we go. So infinity is a state of having no end or limit, often denoted as this sidewards 8. It is the only one, it's the only number that turns sidewards and means something else. You can't just turn like a sidewards 7 and that means something. Sidewards 8 is infinity. So for example, the set of all even numbers, it goes 2, 4, 6, 8, 10, but it goes all the way up to forever, ever. There's infinite of them. You couldn't imagine them. A pattern or expression is said to approach infinity if the value can always be made larger. So if I said to you, there's only 10,000 even numbers, and I was like, the last one is 2 million, for example, you'd be like, no, there's not, 2 million and 2. So because you can always make a number bigger, in this case, then there's always, that's infinity, that's what we say. If I can always give you another number, there's always infinity. Density. Density is the concept that between any given 2 real numbers, there will always be another real number. Thus, there are infinitely many real numbers between any 2 real numbers. Density, then, is quite complicated. Density is basically a short term of saying it, is how many numbers are there between those numbers. And then we compare densities by saying, is there more between these numbers than these numbers? And it's all about understanding the levels of infinity and all understanding that. We're going to get into it, don't worry. And then limit is something we're going to talk about later, is the long-term behavior of a pattern. And so that's something that towards the end of this lesson, where basically we're saying, where does that pattern go? If you know how a pattern goes, where does that pattern go? Where is it ending? Is it going to end at infinity? Is it going to end at 0? I don't know. Is it going to end at negative infinity? I don't know. We'll talk about it. So let's talk about density. So how many of the following can be found on the line between -3 and 3? Well, integers, there's 1, 2, 3, 4, 5, 6, 7, isn't there? So there's 7 of those. Rational numbers, though, we spoke about it a second ago. There are a bunch of decimals all in between here, all different fractions that we can make, right? And as we think about it, if we go, are we done? Have we done them all? Well, no, in between all of them, there's also more, isn't there? And so there's all these, so there's infinite. And then real numbers is all the rational numbers plus the irrational numbers. So it's even more of infinity, but still infinity. And it's really hard to get your head around. But basically, if I have to add more, if there's rational numbers and we said that's infinity, and I talk about the fact that I've got to now add irrational numbers on, then this one right here is more dense than this one, even though they're both infinity. And the idea behind that is that there's bigger infinities than others. And to really mess around with your head, there's actually infinity-sized infinities, etc., etc. Right, here we go. So, density. Notice how there are infinite rational numbers between -3 and 3. But there are more real numbers. Whenever there are more numbers, even in the case of infinity, we say that the set is more dense. So when a question asks, what's more dense, it's only asking what has more numbers in. That's all it's saying. So which one of these has more numbers in? And even if one of the answers is infinity, if the other one has more infinities, if you will, then it's more dense. Okay, I put this here again just in case you need it. As I said, this is something you should always be going back to just in case you forget. But here are some questions. So literally, all I want you to do is think about what has more numbers in it. Even if it's infinity, try and think about what kind of infinity it is. Okay, the set of whole numbers between 0 and 30. If you forget what whole numbers are, there they are. The whole numbers are the numbers from 0 to, 0, 1, 2, 3, 4, 5, 6, right? All positive numbers with 0. So the set of whole numbers between 0 and 30, there's 31 of them, isn't there? There's 31. But the set of rational numbers between 0 and 30, there's infinity. So which one's more dense? This one, because there's obviously more. The set of real numbers between -10 and 10, so we have infinity. Or the set of integers between -10 and 10, well, that's just going to be, is it 21? Because, I think 21, right? -10, -9, -8, 0, 10. The set of prime numbers between 1 and 100, I think, so there's two, just in case you can't remember what a prime number is, it's the only numbers that can be divided by itself in 1 and doesn't include 1. So that's 2, 3, 5, 7, etc., right? But that's obviously missing numbers in between. And then the set of natural numbers is going to be 1, 2, 3, 4, 5, where we're not missing any numbers between, or whole numbers. So I hope that's obvious that this has more. So it's more dense. Right? Because this has, I think it's 21 prime numbers. I can't remember the exact number, but I think there's 21 prime numbers in between 1 and 100. And I think there's, between 1 and 100, there's obviously 100 numbers, right? So 100 numbers is more dense. What do we have more of? The set of even numbers between -70 and 20. So that's going to be 35 of them, isn't it? Between negative 50 and 20 and -20. That's going to be 15. I thought it said positive 20. And the set of irrational numbers between -50 and -20 is going to be infinite. Irrational numbers, they're very weird. You can't count how many there are because every single time you say there might be another one, I could say, okay, what about the square root of this number? And you'll be like, oh, okay, I guess that works as well. So there's always infinite rational numbers between something as well. So yeah, in this case, irrational numbers is the more dense. Okay, so hopefully that kind of makes sense. If it doesn't, it's okay. Like, just think about the concept of if I can always add more to it, then it must be bigger. And if I'm adding more to infinity, even though infinity is infinite, then it must be bigger as well, if you ever get a question that involves two infinities. Anyway, it's a lot more complicated, and you probably will just get questions that look more like this anyway. Okay, where are these sets headed? So have a quick look at these and see if you can tell me the next few numbers, and then tell me where the next number is. So this next one, it doubles each time, doesn't it? It goes 1, 2, 4, 8, 16, 32, etc., etc., and it's going to keep going up until it basically goes to infinity. And we spoke about that earlier. The next one would always be double the one previous, so therefore it must be going up, so it's infinite. This one, it goes from a -1 to a +3 to a -9. So what we're doing here is we're timesing by -3, aren't we? Because from that one to that one, it's times by -3. From this one to this one, it's times by -3, etc., etc. So this one is going to go to positive infinity, and then it's going to go to negative infinity, and then it's going to go to positive infinity and negative infinity. So this one actually ends up in two places, depending on where you stop it. And then this one's a weird one. It goes half, then it goes 2/3, then it goes 3/4, then it goes 4/5, then it goes 5/6. And it keeps going until it gets, let's go really, really high. Let's go 99/100. And basically where it's heading is it's basically heading, isn't it? It's getting really, really close to a 1. right? Half is obviously halfway between 1, 2/3 is getting closer, 3/4 is getting closer, etc., until we get to 99 out of 100, then maybe 999 out of 1,000. It's getting so close that we say it's heading towards 1. And that brings us on to limits. I'm actually going to skip this for a second. We don't need this for now. So another way to think about limits then, and what I'm trying to get around, is if you stand, for example, on the other side of the room from your door, and I said, can you half the distance to your door? So I don't know, let's say originally you start 8 meters away. I don't know how big your room is. And then you half that, so then you go to 4 meters away. And then you half that and you go to 2 meters away. And you half that and you get to 1 meter away. Will you ever make it to the door? Because you'll get 0.5 meters away, you'll get 0.25 meters away. You'll never really make it to the door. But for all grand in terms of purposes, if you keep halving it, at some point you'll be like half an atom away, right? And that effectively is there. It's not quite, but you know you're basically there. And that is basically what we're trying to talk about when we say limits. We're saying, yes, I know it's not actually going to get there, but it's so close to it, that is the limit. And we express it in terms of this. So here we go. In mathematics, the limit is a value that a sequence or relationship approaches. So 1/2, 1/4, 1/8, 1/16 keeps getting smaller, right? Notice how the values are consistently getting smaller. So they are getting closer to 0. What we say then is if we went on for infinite amount of times, infinite amount of like terms, right? Each one's a term, infinite amount of terms, then the number should be getting closer to 0. And so we say the limit is 0. This means as a term gets closer to infinity, so just to be clear about terms, I'm talking about this is your first term, second term, third term, fourth term. We're saying as we get closer to the infinite term, we're going to be something like 1/9999999, right? Which is so close to 0 that we say the limit is 0. And that is the key. So here we go, let's have a look. So what is the limit of 6, 7, 8, 9? It's going to keep going, isn't it? And every single number is going to keep going up. And even the number all the way over here is going to be like 99999, but it's going to keep going up. And so it's going to actually head to infinity. What about this one? This one's always a confusing one. It goes 8.1, 8.001, 8.0001, 8. And if you think about like all the way, all it's going to have is 8.001. It's so close to 8 that we say the limit is 8. I'm going to put a box around what I've said the limits are so there's no confusion here. And actually, I'm going to get rid of this, I think. Let's get rid of the 999. There you go. Okay, what about this one? It goes a half, a third, a quarter, a fifth, a sixth, a tenth, a millionth, a bajillionth, right? What are we getting really, really close to there? We're getting close to 0. And then this one's a weird one. It's just kind of worded differently. But effectively, if I know that n is always going to get larger, what happens to 3n? And you'd be right to say, well, if n's always getting larger, then this one's going to get 3 times larger. And so this one is also getting larger. And that's also it. It's a bit of a weird one, this one. And you'll see why in the final assessment, why I've brought that in there. Okay. If you've understood any of that, try and find the limits for these. I'll go through them slowly in a second, but see if you can have a go. Okay, so here we go. So it's 7.1, 7.01, 7.001, 7.001. If you think about all the way as far as you can think of, what would it look like? It would look like 7.001, which is so close to 7 that we say the limit is 7. And what about this one? It goes half, third, quarter, fifth, sixth, eighth, ninth, bajillionth, whatever. It's getting so close to 0, we say the limit is 0. And this one, if you recognize on the bottom, they're square numbers, right? So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 4, and 5 times 5, 6 times 6, whatever. At some point, it's going to be 5 over a million times a million, which is going to be 5 over 0, 0, 0, 0, 0, 0, which is effectively 5 over an incredibly big number. So it's heading towards 0. So we say the limit is 0. Okay, this one's quite hard. It goes 0.3, 0.33, 0.333. At some point, it's just going to be 0.3333333, right? So that means the limit then is going to be 0.3 recurring. A dot means recurring. It means that 3 is going to keep going on, which you can say is 1 over 3. If you knew that that's a fraction. But you can also leave your answer as 0.3. Either of those are fine. Same here. Negative 2.6, negative 2.66, negative 2.666, right? So my answer effectively is going to be negative 2.6 consistently recurring. And if you wanted to write that as a fraction, you could write it as -2 6/9. And what's nice, by the way, if you ever have a number repeating itself over and over, it's just that number over 9. So here's 6/9. 1/3 is effectively just 3/9, isn't it? Which is where we get that from. And then 1.4 is going to be 1.4 recurring, or 1.4, 1, I don't know why I'm scribbling out, 1 and 4/9. What just happened? Don't do that. 1 and 4/9. Okay, so just a quick recap. Density is which of the things we're comparing has more numbers in it. And remember, there's always more real numbers than there are rational, because real numbers include rational. But when you're looking at rational, real, or irrational, you're just looking at which one's got the most. But in general, most questions are going to be more obvious. It's going to be like, is there more natural numbers, or are there more rational numbers? And one of them's infinity and one of them's not, right? So that's quite easy. When it comes to limit, we're just thinking, if you think of like the 1,000th term, what number is that really close to? And if you know what number it's really close to, then that is the number that the limit is, if that makes sense. Anyway, that is the end. I would say it's one of the hardest things to get your head around in grade 9. And of course, it's in the second unit that we do stuff with. It will come up occasionally throughout the rest of the unit, but all nonsense aside, it's not going to be that hard in the assessment, I promise, in the final assessment thing that I have. So hopefully that makes sense. What I have for you now, if you didn't recognize already, are just a bunch of EQO questions. So if you want to have a go at them, I just went through all the EQO resources I have for the last 2 or 3 years of whenever we've been given examples, and I just try to find them. So if you're doing EQAO this year, because you're obviously you'll be doing grade 9 maths, and so occasionally some schools will still make you do it, then I would have a go at these questions and see if you understand them, and then I'll go through them. What I'll do is I'll put them up for a few seconds, and I'll go through it, and then I'll do the next one and go through it. But if you're not doing EQAO for whatever reason, then you don't have to look at these. Don't worry about it. Okay, here we go. So how many real numbers are there between 0 and 10? Well, people think that numbers, they think about, is there 9, is there 10, is there 100, because decimals, but we talked about real numbers. That's basically any number that we can think of in between 0 and 10. There's infinite of them, isn't there? Because if you think there's ever a limit, I'm just going to tell you another one that you probably didn't think of. So an infinite number is your answer here. What about this one? Which statement about rational numbers is correct? Well, a rational number is always positive. A rational number can be written as a fraction. A square root of any number is a rational number. A rational number is in its decimal form is a non-ending, non-repeating decimal. Let's talk about it. A rational number is always positive is nonsense, because -3.2, that's a rational number, so no. The square root of any number is a rational number. Well, square root of 3 isn't, is it? Because that number goes on forever. I don't know exactly what it is, but it goes on forever, so that's not rational. A rational number in its decimal form is non-ending and non-repeating. That's not true. 1/3 is 0.3, and that does repeat, so that's not fine. But a rational number can be written as a fraction. Well, that's the definition of it, so yes. That is literally the definition of it, so yes. Set C and set D are given. Set C is 3, 6, 9, 12, etc., etc. Set D is set of integers that are multiples of 5. So just to put that in context, that's -10, -5, 0, 5, 10, and then it goes on all this way and all this way. Don't forget your braces. Remember, braces are these weird things. Anyway, select the statements that correctly describe the numbers that are common to both set C and set D. The common numbers are always always divisible of 9. Doesn't make any sense, because literally, if we think about the fact that the next one that's going to come up is probably 30, that's not a multiple of 9, so it's nonsense. Common numbers are always a multiple of 15. That makes sense, because this is 5, this is 3, so it makes sense they're 15. We'll come back to it. The common numbers are always going to be odd numbers. No, we just said 30, so no. There are no common numbers. No, that's nonsense. So yeah, it's B. Because if it's a multiple of 3 and 5, it's going to be a multiple of 3 and 5, which is 15, isn't it? Okay, what includes 0? That is your natural numbers. Wait, hold on, no, it's not. Yes, it is. No, natural numbers. No, it's not. No, it's not. That's not. It's your whole numbers that include. See, even sometimes I forget. Rational numbers, no. Integers, yes. Real numbers, yes. It's not natural numbers, because natural numbers are 1, 2, 3. ... Not 0, 1, 2, 3. Correctly, blah, blah. Between 10 and 20, there are infinite many restaurants. Cool. 3.78 times 10 to the minus 4. Remember, you put 0, 0, 0, 0, 0, 3, 7, 8. You just go back 4, 1, 2, 3, 4. So it's going to be 0 point with 3 zeros. So it's this one. 253. So you write 2.53 times 10. Decimal point goes here. Count 1, 2, 3, 4, 5, 6, 7. So it's positive 7. 3.5 times 10 to the 5. Remember, you just write 3.5 and you just write a bunch of zeros after it. And then you go 1, 2, 3, 4, 5. So it's going to be 3, 5 with 4 zeros after it. So this one. Which one's negative 5 over 6? So if we just simplify all of these, that's obviously not the same. This one would become 5 over 6, but that's not got a negative. This one would become positive, wouldn't it? Because I've got a negative and a negative, which makes it positive. So this would be 5 over 6. And this one is just, you can bring the negative out in front, and then 10 and 12 can both be divided by 2. And that would get me 5 over 6. And that is exactly what it says. So that's that one. Okay. Hopefully that was helpful. If you didn't quite understand it, don't worry. Have a look at the quiz and see if you understand, because hopefully that will make it more. And if not, email me if the quiz doesn't make sense and I can try to go through it again. Okay. Thank you. Have a good day. Bye-bye.